Hello everyone, my name is Pranali Surkar and I'm working as an assistant professor in the Department of Electronics and Communication Engineering at Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. I welcome you all for the video lecture series which is based on the course Digital CMOS IC Design, and today we are going to discuss about the topic VLSI Design Flow. As we have started earlier the unit 1 and we have discussed 3 topics before. We have discussed the issues in the digital integrated circuit and quality matrix as well. And again, we have seen some IC technologies, MOS, NMOS, PMOS, and CMOS, which is complementary metal oxide semiconductor, as well as BiCMOS technology, which is the combination of bipolar and CMOS. So now the main part is VLSI circuit design process, in which we are going to discuss about the VLSI design flow. Now, VLSI stands for very large scale integration. We have already seen the definition of integrated circuit. So where we are fabricating millions and billions of transistors on a single silicon wafer. So basically VLSI is the integration, very large scale integration. Before that we have discussed different integration levels, from small scale integration, then medium scale integration, then large scale integration, and now it is VLSI, that is very large scale integration. So based on the transistor count it processed, and here also it is this VLSI VLSI is the process of designing and fabricating integrated circuits that contains millions and billions of transistors and on a single chip. Or either we can say that active and passive elements, components we are integrating together on a single piece of semiconductor. Mainly we are using the silicon. Now what it enables the complex functionality in the compact device, because nowadays we are using the portable devices and which are very compact in size. So it will enable the complex functionality in that particular compact devices which drives the modern electronics. Now, what are the key principles of this VLSI? So why we are going towards the VLSI? So main reasons are, it provides the miniaturization, means it will create a very small in size devices, and which again it gives you the proper functionality as well despite of the smaller size. Then performance enhancement is the another key principle. So as we are integrating billions of transistors, so it will give you the better speed and better performance. Then reduced power consumption means VLSI we are using for the lower power consumption, low power devices, because power consumption is a very critical issue, very crucial in the modern electronics. So it will provide you the lesser power consumption. So then hierarchical design means it will enables the whatever the high level design is there, we are basically divided into the smaller parts. So that is nothing but the hierarchical design. Then PP optimization is a very again important things. So engineers are working on that power optimization, performance optimization, and as well as area, so to meet the specific requirements. So this is all about the VLSI. Now we will move towards the VLSI design flow. So first we'll discuss that what is VLSI design flow. So VLSI design flow is nothing but the systematic step-by-step process. Means whenever we want to create any integrated circuit, we have to follow some steps. So that altogether process is nothing but called as VLSI design flow. So as this VLSI design flow is divided into two main parts. The first part is nothing but the front-end process, and another part is nothing but the back-end process. So back-end and front-end. So this flow, VLSI flow, is divided into the front-end and back end. So now what front end will do and what are the process involved in the back end, that we are going to see in details. So front end, what it will do, it deals with the functional and logical aspect of the chip. So whatever the functionality and logic design will be there, so including the specifications, that comes under the front end. Then what back end will do, so it will deal with the physical implementation of the chip and physical implementation of the components and device, physical implementation of all the components on a single on a silicon wafer. So this is nothing but the front end and back end. So we are going to see what are the process, what are the steps involved in the front end as well as in the back end. So how the VLSI flow starts, the first step is nothing but the system specification. We are going to see the all the process in details. So first process, the first part of this VLSI design flow is nothing but the system specification. Then after system specification, another step is architectural design, then functional design and logic design, circuit design. So all these four comes under the front end. Okay, so these four steps comes under this front end, and all these are in back end. Okay, now whenever the circuit design, after the circuit design and creation of the get level netlist, so we'll go for the physical design. But inside that physical design, we have all another steps. So first will be partitioning, floor planning, then placement and components, clock tree synthesis, which is nothing but in short we call it as a CTS, signal routing, and timing closure. So these all 6 steps are involved in the physical design. Whenever the physical design completed, then we have to verify that physical design whether it is meeting the specifications or not. So after verification, then we'll do some layout post processing. Then we'll go for the fabrication after this processing, and then the last step will be packaging and testing, and after that it will go to the foundry. So as we have discussed, as front end design flow, it deals with the functionality and is where these initial design concepts that are transferred or translated into the detailed hardware description. So front end deals with the hardware description language, and from the specifications to the up to the gate level netlist. So the first step involves is system specification. So we can call it as system specification is nothing but the requirements. So whenever we want to design something, or whenever we want to design any integrated circuit, so we have to first focus on the requirements or specifications. So how these specifications will be categorized. So in this we will see the what is the functionality of that particular device or block, then what is the performance targets, it deals with the speed and all. So after that how much is the power consumption, and then how it will interact or interface with the different components, other different components. So what's system specification is defined. So whatever the overall goals and requirements of that particular chip, that is defined in the system specification. Now for as example, if you want to design the processor for any what we can say any smartphones or like that, so then what will be the specification for that? So as it is a portable device, power is the main issue, or is a crucial aspect. So we need to focus on the power consumption. Then as here I have taken the example of new smartphone. So if we are going for the to build any new smartphones, or even if we want to purchase the smartphone, then we will focus on whatever the battery consumption is there, means power, then whether it is faster or not, then what is the camera resolution, what is the battery backup, processing speed, prices. So all these are nothing but the system specification. So whenever we want to build any IC for any particular application, so the first is nothing but whatever the customer requirements. So which is the first and primary stage, or we can say the starting point of the VLSI design flow. So that comes under the front end. Another one is architecture design. So in this architecture design, designer focuses on the architecture or the structure. Then in that, whether they are using the RISC or CISC processor, is RISC or CISC architecture. That depends on the application and the designer. So this is again the crucial initial step of this particular VLSI design flow, which define the high level organization structure and how the system is behave, or the chip will behave, means overall behavior of the chip. Now what it will do, so it will translate the product system level requirements, which we have seen in the first step, into the functional blueprint, and which will guide the entire development process. After that, what engineers will plan, so it will plan the chip architecture, and where they will decide the major functional blocks, and they will see the how the communication methods and protocols are included among the each of the blocks. Basically, it will deals with the interface. Then the third design process, third step in the design process is functional design and logic design. So in this functional design, it will basically deals with the RTL model. So RTL is nothing but the register transfer level. So this is the step which involves the design of IC with the help of hardware description language. So there are two hardware description language we are going to see, that is VHDL and the Verilog. So we have to write the code, or we have to write the Verilog code, or else we can write the VHDL code by using this language. And we are basically by writing down the code, we are specifies the functionality of the block. Then it will focuses on the behavior and how it will interact with the registers. So basically how data flows in between registers, that is nothing but the register transfer level. Another is, after writing down the code, we have to check, or we have to verify the functionality. Means we have to check whether we have whatever the code we have written for any design, whether it is correct or not. So we have to simulate that particular RTL code, and we have to test whether to ensure that whether it will meet the system specifications or not. So it is basically the time consuming process, and it will validate that whatever the design logic we have written in the by using the hardware description language, whether it is correct or not before going to the synthesis. So another after verification, we are going for the circuit design and logic synthesis. So there are different logic synthesis tools available in the market, so which is used for to create the gate level netlist, whatever RTL code we have written, which is translated into the gate level netlist by the use with the use of logic synthesis tool. So this, what is that gate list? Netlist is nothing but the blueprint of the design. Means whatever the code we have written in the Verilog language or any VHDL. So we have to verify this code. After verification, we have to create gate level netlist. Means whatever, for example, whatever code we have written, according to that, it will create a circuit, or it will create a logic design with the help of our basic logic gates. So which is already predefined in the library. So basically this is the first step of the physical representation, or we can say that it is a last step of front end also. Then after front end, after creating the gate level netlist, we have to go towards the back end process, means actual physical design. So back end process deals with the physical implementation, and it is a process of converting the logic gate level netlist we have created in the front end into physical layout. But as we have discussed and as we have seen in the flow chart, physical design is again partitioned into the 6 steps. So the first step is nothing but the partition. So as its name indicates, partitioning means we have to partition, we have to we have to divide the complex blocks into the smaller blocks. So partitioning is nothing but the process where we are dividing the large and complex circuit into the smaller and more manageable sub blocks and modules. So this is nothing but the partitioning. So what it will be, how this partitioning enables. So this will enable each segment to be designed, analyzed and optimized independently. Whatever the blocks we have divided in the smaller blocks, so that will be optimized independently, and which will improve the functionality, which will improve the efficiency as well as the complete design process smoothly. After partitioning, we have to see the position of the chip. So basically floor planning is nothing but the chip planning. So what we are going to do in the chip planning is basically we are planning, or we are strategize the arrangement of the various sub-circuits, modules and IP blocks. So IP blocks are nothing but the intellectual property. So this is nothing but the third party integration. We can, as we have discussed earlier also in earlier class, third party integration is nothing but we are using the another vendor blocks in our main design. So within the physical layout chip, so we have to strategize and we have to arrange all these sub blocks and modules and IP blocks into the physical layout, within the physical layout. Now this step defines the shape, then shape of the design, the complete design, orientation and relative positioning of the components on the chip. So as well as basically it will deals with the location of the external ports. And so what we will get after the floor planning. So what floor planning do? So floor planning optimizes the chip area efficiency, and it will minimize the interconnection delays as well. So if we do the proper floor planning and if we arrange the all the circuits and modules in a proper way, then we can have the better area efficiency. Means within the very less area we can arrange all the components, and it will minimize the interconnect delays also, and it will enhance the overall performance by ensuring that modules are placed in a proper way, which will facilitate the efficiency, routing and power distribution. If the components are not properly placed, then it will be create to circulate the power in each of the block. Then after this floor planning, we'll move towards the placement. So in this placement, this is the stage where all the precise special locations of individual cell within the each block are determined. Means here we are again seeing the cell positioning, and which will meet the physical constraints, such as whatever the wire metal wire we are going to use for the interconnections, that wire length, then routing congestion is nothing but the if we placed all the components are very near to each other, then it will create the congestion and performance goals also. So proper placement, what it will do, so it will minimizes the delay, then it will improve the power efficiency and contributes more compact and functional chip design, which will minimize the interconnect paths as well if we arrange the cells in a proper way. Then this is nothing but the clock tree and network synthesis. So this in the clock tree synthesis, we are mainly focusing on the timing and clock, whether the clock is whether we are providing the clock to the each of the block or not. So it is the process of designing the clock distribution network within the chip to ensure whether the clock signal is reaching to all the parts of the circuit and each of the block, whether it is a sub block or main block, for the required precision. Now if we are not doing the proper clock synthesis, then we may face the issue of clock skew as well as we have to in this content we have to see the clock gating also. So clock gating, we have discussed, if whenever clock gating is basically the power reduction technique. Whenever we should keep this clock whenever it is necessary, otherwise we can disable the clock. Even clock skew is nothing but the it is a difference in the arrival of the clock. So if we are not properly managing the clock inside that within that space, so we may face the clock skew issues and a signal delay. So to meet this, to overcome these requirements, we have to focus on the timing, proper timing requirements. Then well-designed clock tree ensures that the operation should be synchronized with across all the chips, which will be improving the performance, as well as it will minimize the power consumption if we apply proper clock gating. Then signal routing is nothing but how these blocks are connected with the metal wire. So these metal wires are created to connect the placed cells and blocks according to the netlist. So this basically divided into two types. First is the global routing, another one is the detailed routing. So global routing provides the high level plan, where detailed routing it optimizes the final layout of the chip, and by minimizing the routing congestion. Then timing closure is nothing but the process where we have to see whether the timing is correct, or whether timing is correct, or whether the design is fine tuning with each other components, and specialized placement and routing techniques to ensure that timing requirements are met, whether whatever the specifications we have given. So for that particular requirements, whether the timing is proper or not, that we have to see, we have to check. So this will include the timing related issues like data delay paths. So we have to adjust the placement of the cells to minimize the critical path delays. Critical path is nothing but the longest path without any delay. So we have to minimize the critical path by proper timing closure. And again, we have to refine the routing to achieve the necessary performance level. Then what timing enclosure will do? So it will ensure that circuit operates at the desired speed without any without violating setup and hold time. So setup and hold times are the constraints where whenever setup time is nothing but the minimum delay time before the clock edge, and hold time is nothing but the minimum interval of the delay time after the clock edge. So we should not disturb the setup and hold times constraint. So for that, timing closure is plays a very crucial role. Then after completing all these 6 steps, we have to verify whether the physical design we have built is correct or not. So for that, we have to verify this whether it is meeting electrical as well as functional requirements, whether the design is functionally correct or not, that we have to see after the after completion of the design. So this comes under the physical verification. So after that, layout post processing, in this DRC and LVS we have to check. So physical verification includes these two processes, DRC and LVS. So DRC is nothing but the design rule check-in, which follows all the foundry rules. Means whatever the foundry rules are there, whatever the minimum spacing between the wires, whether if you are whatever the distance between the two metals. So there are some different design rules and different foundry rules that we have to check. Then layout versus schematic is nothing but LVS, which verifies the physical layout, whether whatever the physical layout we have created, whether it is matching with the gate level netlist we have created in the front end. So that it will ensure ensure the it will ensure that whether the physical layout matches with the logical gate level netlist or not. After this process, we will move towards the fabrication. So fabrication is nothing but the process where we are actually manufacturing the chip. So again, it will involve many steps like etching and etching process, photolithography process. So that comes under the fabrication process. So after verification of the layout, all the files are sent towards the foundry, which will manufacture the process and actual silicon chip using all these photolithography, doping and etching technologies. So after completion of the manufacturing process and fabrication process, the chip is we have to use some proper packaging techniques for the chip. So after dicing, functional chips are carefully packaged so that it will be protected and it will be connect them for the electronic devices. So packaging is determined early design process to meet the specific application. So it will all includes the cost constraints as well as form factors requirements. Now after the packaging as well as testing also. So chip testing, here we have to again see the functionality and manufacturing test whether they are functionally proper or not. So it will ensure that chip again meets the specific requirements which we have already discussed in the front end. So whether it is working properly and meeting that functional and specific all the requirements properly or not. So this will involve whether the IC we have fabricated, is there any defects in that IC or any electrical shorts, or whether it is signals coming correctly or not. Is there any power issues involved in that. So we have to check all the parameters, and then if any faulty or any defective chip is there, then we should not sell, we should not we should not keep as it is. We have to discard that, and then we again either we can discard or we have to rework on that, and then only it will be comes in the market. So this testing is the last process of the VLSI design flow. So this was all about front end as well as back end in the VLSI design flow. So it will start with the specification and it will end with the packaging and testing. Thank you so much.